So Mitch is from Rice University, and he's looking into how you can actually address the phasing problem using machine learning. And I actually am very excited about that because I looked into that about 8 years ago. And now obviously algorithms have progressed. So I'm looking forward to your talk.
Thank you to the organizers for inviting me to sort of tell you about our progress and sort of exploring, what can we do with machine learning and the phase problem. And so I want to sort of give a brief sort of background a little bit and some prior work that sort of inspired us to go ahead and try to do machine learning phasing, and give a brief review of Patterson maps and some of their properties, and a super brief introduction to some machine learning concepts, and then talk a little bit about our dialanine and dipeptide trials and how we've moved on to 15 residue peptides, and sort of what our next steps are in trying to move from sort of toy problems to real problems. So as we all know, the phase problem is where we can't image from the diffraction pattern directly, and the common methods used have been isomorphous replacement, anomalous dispersion, and molecular replacement. And with AlphaFold, that's really the primary way that I think most phasing is going to be done for the going forward. And so we were really sort of inspired by a paper that came out, a preprint from David Hurwitz, where he looked at sort of random groups of 10 atoms and then tried to phase them from Patterson maps using a convolutional network. And so just a reminder for the Patterson map is, a Fourier transform that doesn't require the phases, and it just uses the squares of the amplitudes. And so some of the properties, we can just use intensities to that we measure directly, and we don't have to we sort of bypass the phase problem to make that initial map. The map sort of gives us interatomic vectors between the atoms in the cell, and you're going to have sort of n squared peaks. So, when you get to large structures, you have a lot of peak overlap. And so traditionally, Patterson methods work well for small numbers of atoms, and it's been used a lot in sort of substructure determination for anomalous scattering. But the question is, can sort of machine learning sort of get around some of this? There's also some ambiguities with Pattersons in that they're invariant to translation of the entire unit cell, and centrosymmetric structures are going to give rise to the same Patterson. Hurwitz sort of addressed this by using a mixture of both his true structure and the centrosymmetric structure. And we sort of approached it differently by saying that since proteins are only a single hand, if we only give the algorithm a single hand, will it sort of learn to sort of produce our desired hand. There's also sort of an origin, a question as to which peaks correspond to which origin, which can give rise to multiple structures giving the same Patterson map. So our goal with this project was to sort of bypass the phase problem. We wanted to sort of predict the electron density map just given the input intensities. And we were going to start that process by using the Patterson map, and which that map is conveniently the same dimensions as the electron density map. And so then our we were going to start with using a neural network to try to map from that Patterson map into the real space electron density map. So just a super brief introduction to machine learning. Our goal is sort of to define this black box. And so what we have an input and we have a desired output, and we needed to design a function that can get us from one to the other. So the loss function is sort of what ties it together and sort of how we train the function. And so in our case, it's sort of a regression problem where we're trying to sort of bring the function closer so that each cycle it gets closer to predicting our desired structure. So one way to sort of think about a convolution is it's sort of, you have a kernel or a filter that sort of marches along the structure and is essentially just sort of a matrix multiplication as you go across the image. And so, we're sort of familiar with these in terms of using edge detection and things like that are sort of similar sort of filters that are applied to images. But in the case of machine learning, instead of using sort of a handcrafted kernel, we are going to sort of treat each of the weights of the kernel matrix as variables and then try to determine what those weights should be to sort of give us extract the desired features we need to sort of produce the electron density map. So this was sort of our first model that we produced. So there was an initial encoding phase, and then that goes through and is cycled a number of times in a learning phase, and then a decoding phase at the end to sort of come out with the map. So we need data to sort of train it. So instead of taking random atoms as Hurwitz did, we took dipeptides from PDB structures just in random orientations and then put them into a P1 box. And we would then calculate structure factors from that model and use that to make the starting Patterson map. And then we would normalize the Patterson map to -1 to 1 so that we can use a tan-H activation at the end. So initially we started with just dialanine, and we just used the standard mean square error as the loss function, and we sort of monitored the Pearson correlation as we went along. So Hurwitz used sort of an enlarged cell where the atoms were only in the center portion of the cell. And so we did that initially using a 20 by 20 by 20 cell, and then moved on after that worked and were able to go to a tighter cell. And this is sort of from that second tighter cell that we were able to sort of, the prediction is in green and the model is in blue. And so we were able to even the very low ranked structures are fitting fairly well, and then until you get to the high rank structures, they fit very, very well. And so encouraged by that success, then we went to, oh, sorry, this is the sort of phase error for the, and so at low resolution, the phase error is very low, and then as you get to higher resolution, we lose some of the details. So So encouraged by that, we moved on to a dipeptide data set where we were looking at all possible dipeptides. And in order to do this, we increased sort of the number of training examples. And we decided to also include the Pearson correlation coefficient as part of the loss function as well, just to see if that helped improve our training. And we found that indeed we could get to a reasonable sort of phase error over time. And so this is sort of a summary of some of our early work. So the dialanine structures and then moving on to the dipeptide. And then, so initially they were all sort of fixed unit cells. And so we knew that to get to real structures, eventually we'll have to tackle more variable cells. And so then we sort of redid the dipeptide structures, putting them in variable size cells, and then explored different ways of sort of training and retraining in order to improve. And then at that point, we were sort of also exploring different models of how we can sort of different machine learning models. And so we added a transformer model and found that we could get better results using the transformer with less required training cycles. And so here's just sort of an example of the initial UNet convolutional network results compared to the same UNet, but then in addition to giving it, we decided to try to give it some more prior information where we gave it a single conformer of each amino acid just by using the COOT get monomer function to sort of get sort of a standard representation of the amino acids that were in, since we figured we would always know the sequence of the structure we were trying to solve. So by doing that, that gave us an additional channel into the network, and that it improved things a little bit. But then the transformer model did an even better job of reproducing the structures. And so this is sort of looking at the phase error again. So the transformer model is much better across all resolution ranges. And so here's a brief overview of sort of what the transformer model looks like. So it's sort of bookended by convolutional network. So there's a convolutional network that does the encoding, then we have the transformer layer, and then another convolutional network that does the decoding. And then we have each of the sort of standard sort of partial structures of the standard rotamers that are input come in, and then we have a one-way attention mechanism that goes from the partial structures to the Patterson part. So then after success with the transformer, we move to a larger structure. So now instead of looking at just dipeptides, we're extracting 15 residue segments from PDB entries and then using that to create variable sized unit cells. And then we So, sorry, initially the 15mer, we put in a fixed unit cell, and throughout clash cases where they didn't pack, and there was overlap, and we found that we could get sort of a Pearson correlation around 0.82 after about 80 epochs and 20 recycling epochs. So for the top rank structures and even the middle rank structures, the fit was fairly good, and as you got to the lower rank structures, it sort of generally had density in the right places, but the connections were wrong, and there was some noticeable problems with it. So we sort of looked in to see, how many of these could sort of an auto tracing algorithm solve. And so we did a couple different ways of doing that. One, we used sort of the Phoenix auto build, where we could sort of limit it to where we either use just a fixed map and didn't do any density modification, or where we allowed it to do 2FO minus FC recycling from the auto traced result. And then we also did shell XE poly A tracing, which also included density modification. So depending on which protocol we use, we found that 75 to 85% of the test cases could be successfully traced. And so then at that point, we went back and sort of added some more variability to our cells by adding not just sort of fixed 90-degree angles in P1, but adding some additional variation in the angles in unit cells. And in this round, we again sort of got to 0.82 sort of mean phase error. And again, we're able to sort of get some predictions that match fairly well. And then again, we can use that for auto building. So we've since done some additional modifications. We've, instead of just only considering P1, we've also expanded to P21 as well. And then with the 15-mer structure, and then just for testing purposes, since the dipeptide models are much faster to train, we can use those for some exploring sort of ways of tuning the model. And so we've done as many as 5 different space groups at once, and found that we're able to properly recover the space groups. And we've tried it both with including space group functions in the loss function, and also with just allowing the model to sort of learn the space groups, and found that very early on in the process, it gets the symmetry of the output map matches the expected symmetry of the system. We've also done some additional, in addition to sort of doing retraining, where we take the output of a round of predictions and using that as an additional channel and input for another retraining run. We've experimented with doing density modification on those initial predictions before putting them back in. And we've actually found that adding additional, having a variability as to whether we use it directly or, well, so here's sort of the recycling flow. So after we come out of our sort of prediction, then we have an opportunity where we can take, after we take our prediction back in as a starting input, or we can run it through ShellXE and do some density modification and then run it back in. But the ShellXE maps are a little bit too much like the ground truth, and we found that it actually was beneficial to add some noise at that level and add some probability as to which map we sort of pass through, and that essentially gives us sort of a data augmentation, since the number of training examples is not very large for the size of the problem. And so that allowed us to sort of move from sort of 0.82 to 0.9 in our correlation coefficients. And we've also sort of started exploring with adjusting the resolutions, and found that even if we cut the resolution to 2 angstroms, that we still sort of do quite well in terms of our predictions. So sort of our ongoing work that's going on now is we're trying to generate things with smaller solvent contents, because currently we haven't been packing quite as efficiently as real crystals. We sort of have a little bit excess space in the unit cell, which sort of makes it a little bit easier to solve. And we are also looking at other ways of trying to use additional prior information that we may have in our efforts to, and we're working to move to larger cases. So the P21 case, we essentially have 30 residues in the unit cell, and we're looking to move closer to 100 residues in our next data set that we're working on generating now. And so some acknowledgements. So this is the thesis project for Tom Pan, who's jointly advised by George Phillips in the Biosciences Department and Tassos Kyrilidis in the Computer Science Department. Chen Dunn helped with the first implementation of the transformer for the dipeptide case, and Evan has been helping with some ablation studies and trying to better understand parameter optimization for the work. So thank you.
Thank you very much, Mitch. Have we got any questions?
Hello, Mitch. Thank you for this work. I was wondering, do you give your algorithm all the low order reflections with or without bulk solvent compensation?
Yeah, so currently it does have all the reflections.
I think that's an advantage one never has with real data.
Sure. Yeah, and so, currently these structures can be solved by other methods because they tend to have a little bit higher solvent content. So we're sort of trying to make steps in the right direction, but we're not saying that we're there yet. Yeah.
Hello, Martin Mali. Please, can I ask you, I'm sorry for a bit naughty question. I'm just wondering, as a user, what are you targeting when we compare the phasing with phaser, or the usual methods? Is it to the speed, or to get to phase structure which is not easy to solve? Because we heard, like from 100 structures, Tom Terwilliger can solve 90.
Yeah.
And the other 8 can be solved by Vladek.
Yeah.
So we have 2.
Yeah.
You are targeting to those 2? Or?
So right now it's more sort of a theoretical, like what can we do and what can we learn, and sort of then we're sort of also thinking about how can we apply it. And so we're also thinking about, can we use it for sort of model completion purposes and things like that as well. But yeah, so it started out sort of as a theoretical, what can we do with machine learning and how can it be beneficial? But yeah, so still you're going to want to use AlphaFold for most of structures.
Any more questions? Anything online? No. So yeah, so I think that's it for this session.